So I'll be talking about continuous heterogeneity. It actually, a lot of this applies for also kind of discrete heterogeneity, but we'll take the point of view of continuous heterogeneity. And so that's my model for Cryo-EM. So it's these guys, just because it's easier to explain them than what molecules do. But we'll get back to actual molecules. So what is, so I think about these as cats, but you might need a lot of imagination. These are ears and a tail. And what we have in Cryo-EM is we have these 3D objects, and we get these two-dimensional projections of them with a lot of noise, with filters on top of it. And we need to get three-dimensional objects out of this, or to get many conformations of these three-dimensional objects. So we have different cats, so we'll get to that. Okay, so just to set up some notation, so we have this density or electric potential function, and it's easier to see what happens in the Fourier domain. So every image is just the. Okay, I must warn you in the first row when I wave this. Okay, so we have this three-dimensional volume. We're rotating it to a certain direction. We're adding the shift, which happens to be just a filter in the Fourier domain, and we add the CTF, which is also just a filter. This is phase. This is amplitude. So we can take everything and make this into this kind of an operator form. So we have this three-dimensional object. We're hitting it with some kind of an operator that includes everything, and we get an image. And out of this, we can build this compute likelihood function for each of the objects, basically comparing the object to what we actually observe in an experiment. And we can turn all of this into this big Bayesian model where we're trying to estimate the object with these with these latent variables. And then we run stochastic gradient descent, or we run expectation maximization. And the problem, like I said, I'm more interested in the continuous heterogeneity problem. So that's an example of continuous heterogeneity. So we have this cat, and it's turning its head, also turning its tail a bit. And we want to figure out what's going on there. So what do we usually do? The classic thing now is to think about this as basically having, say, two or maybe more independent objects in there. So we have volume number one, volume number two. Technically, they don't have to be aligned. They can be sort of do whatever they want. And then we basically just add this something that identifies which one of the objects we're looking at. So we're extending the same model and kind of using very similar machinery. And if it's a larger family of objects, or a continuum, we usually think about this as trying to discretize this continuum and think about these as sort of independent objects. And there's several, there's been several ways of looking at heterogeneity. So one is what I kind of started talking about now, which is looking at these as individual molecules, and there's various masking techniques. More recently, there's this idea of looking at multi-body, so looking at several rigid objects that are moving. I guess we've had a lot of talks about the covariance and manifold learning, and there's a recent survey that talks about additional methods. So I'll mention some of these, the connections to some of these as I go. So the place I like to start when I think about continuous heterogeneity is what is the question first? So what are we trying to solve, in the sense that if I gave you a solution, what would that solution look like? What would be the form of that thing? I mean, ideally it might be molecules, but maybe it might be the actual atomic structure, but a step back, and terms of densities, what would that mean? Maybe we'd like to see something that looks like a movie or something like that. So we'll try to formulate what's the question first, and then try to figure out if we can actually solve that question once we pose the question. And to look at this, let's take a step back and look at the three-dimensional objects and two-dimensional objects. So we've seen that we can actually learn a lot from just the two-dimensional projections. We've had talks where demonstrating just the two-dimensional projections. So why do we bother going from class averages to 3D objects? And there's several answers. I'll go actually from the bottom top. And one is we kind of actually want the three-dimensional structure. There's some information there that we can't directly see from the two-dimensional objects. There's these rare orientations that we don't see directly, but we can sort of fill in this information because we have these common lines. There's a way that we can regularize our data through the spatial constraint, frequency constraints, this 3D object introduces these additional constraints on the two-dimensional on the projection. So there are the common lines. There's things like that. So there's various reasons why we don't just go with the two-dimensional class averages. We actually go to these three-dimensional objects. So we'll try to generalize that idea. So first, how do we represent the three-dimensional objects or the three-dimensional molecules? Usually, we'll write this as some kind of a sum of basis functions. And it's not necessarily obvious from when you look at this from these samples on the grid, but these are also what's hiding behind it in the signal processing that we're doing is these some kind of basis functions. And these help us regularize the object because we're assuming that the object is band limited to some extent. And we're assuming that it doesn't live everywhere. We're assuming that it's kind of contained in compact domain in space. Well, you can't really have both, but as much as you can. And if you know me, you know that at this point I can't resist plugging in, mentioning that there's a right way to do this. There's the right basis of functions, but we don't have time to talk about them. But if you want to talk about them tomorrow, happy to talk about them. They're basically representing these constraints. So back to this. So we have some kind of a representation of our object as a linear combination of basis functions or as these points on these grids. And again, if we have two objects, then we just have these two different sums. Each one of these sums represents one of the objects. And if we have this family of objects, then each of them has its own different sum. So, but there's something kind of not very pleasing in the way I just like picture this here. So, I mean, somehow this is a little bit more pleasing. But why is it more pleasing? Because what I did is I aligned them and organized them by the direction where the head is turning. But I didn't do anything. I mean, it's really the same functions, just rotated. So why is it more pleasing to us? And it kind of takes us back to this question of what can we do with class average? What can we do with this 3D object that we can't do with the class averages directly? So with the class averages, we can't use this if they're not kind of organized in any way. One class average doesn't tell us much about the other class average. It's the fact that we're putting them together, we're aligning them, we're saying like how they should fit together that tells us that helps us use one to say something about the other ones. And that's sort of what makes this more pleasing to us, because what we can actually do here is take, so from going from two-dimensional images to three-dimensional images, we switch from two-dimensional basis functions to three-dimensional basis functions, from two-dimensional functions to three-dimensional functions. Here we can switch from three-dimensional functions to four-dimensional functions that capture this continuum or kind of this smooth transition between different states. So there's this additional information that exists just by the fact that we're aligning these things and ordering them, much like this additional information exists and can be used when we go from class averages to three-dimensional objects. So we call these things hypermolecules. So it's just higher dimensional functions. And it can be any basis functions that you, it can be any function, any high dimensional function at all. An easy way of writing them is to write them as a linear combinations of four-dimensional basis functions. An easy way of getting four-dimensional basis functions is choose your favorite three-dimensional basis functions and multiply them by some one-dimensional basis function. So it can be polynomials, or it can be sines and cosines, but it's sort of really generalizing similar ideas. And you can really generalize this to higher dimensions if you have more complicated heterogeneity by basically introducing higher dimensional basis functions, for example, by multiplying by several polynomials in several additional dimensions. So for the questions of why do we do class averages, why don't we just stop at class averages and we go to 3D models? The same reasoning for why don't we stop at 3D models and go to hypermolecules. So hypermolecules allow us to introduce additional constraints just by the fact that we require some kind of continuity, some kind of relationships between these different states, which we can enforce in many ways. Some of them are, for example, the basis functions or some other forms of regularization. There's information about rare states in the same sense that it's not as general, but it's in the same sense that you can view kind of rare viewing angles. The fact that you have, I didn't put the continuum here, but if I have, well, this cat and this cat, they tell me something about the cat in the middle, even if I see fewer examples of that cat in the middle. But I can use the relationships. And it's kind of actually what we want to see at the end. What we want to see at the end is some kind of a movie, or we want to have some kind of knobs that we can turn and move the object from one state to another. So all we've done is basically going from this likelihood model that says I have these images, I'm comparing them to 3D object with projected to a two-dimensional image. What we're doing here is we're saying, well, I have this two-dimensional image, and I'm comparing it to this high-dimensional volume that I'm projecting to a two-dimensional volume. So it's very similar. And if you compare this to the discrete case, basically all that happens is it actually takes a very similar form to choose your to what we did here, which was to choose one of the volumes, one of the discrete volumes. But what's hiding behind this is the fact that this hypervolume enforces these relationships and between the different states. And that can be very informative. So that's kind of we took this idea and that's like the original experiments we did with this, that's where the cats come from. So we had these 50,000 cats. We didn't do this with the CTF and stuff, but there was a lot of noise. So we took these 50,000 cats and we threw this into a machine that, well, we have new algorithms, so I won't talk much about the algorithms behind this. But this is what comes out of this reconstruction of this four-dimensional cat. And what we're looking at is three-dimensional slices of the four-dimensional cat. So what we can see is that we can see these, we can kind of characterize the movement. It's kind of interesting that it's aligned in a different way. That's an ambiguity that's actually naturally created. And these are printouts of these 3D slices of the four-dimensional cats. Unfortunately, we don't have 4D printers yet. So this is very generic. You can sort of represent basically any function that does anything in this form. In a sense, there's a sense in which it can be too generic. Why is that? So as we go to higher and higher dimension, and why would we go to higher and higher dimension? So this is the pretzel, and I'll get to real molecules. But so this is the pretzel, and this pretzel has these two arms moving around. I should really put this down when I'm waving my hands. Okay, so I warned you. So it has these two arms flapping, okay, and they're flapping independently. So each one of them has this one-dimensional parameter saying where it can be, and so there's two-dimensional parameters, right? And if we went up to, I think, like 15-dimensional object when we were working on something, we couldn't solve it yet, but it means that however fast your Cryo-EM facility is, you don't have enough pixels to even fit all the parameters in it. So why am I saying I'm working on 15-dimensional objects then? It just doesn't make any sense. The reason is that the number of coefficients basically, so if we think about this as voxels, and we have like n cubed voxels, and we think about the way we represent the functions in time, the degree of the polynomial, for example, suppose it's q, and then we have d dimensions, this grows exponentially fast. And it sort of makes sense, because if there's so many possible states or conformations that we want to look at, we would need to have at least some information about like some of them, right? And since there are so many of them, how can we cover all of them? Additionally, there is a computational problem. Even if we had all the data in the world, we would have to, if we're doing something like expectation maximization, technically in like pure expectation maximization, what we're supposed to be doing is looking at every image, comparing it to every orientation at every state. And there's a lot of states. There's a computational complexity to it. And the answer is in the anatomy of the pretzel. So we can decompose that pretzel to this rigid. It doesn't have to be like a very well-defined partition, but we can say there's this rigid object in this somewhere in this yellow ball, and we can say there are these some kind of heterogeneous object somewhere in this blue ball, and some kind of an heterogeneous object in this yellow ball. And what we've done actually is, and if you think about it in terms of manifolds, we decompose this generic manifold that can be high dimensional intrinsically to a product of different manifolds. So we decompose this object. And if you look at the number of variables, now it grows just linearly in the number of dimensions, or the number of regions that we have. So this type of modeling allows us to reduce the number of, to make this problem tractable. And don't get me wrong, if you have, so data is power, right? I mean, if you have tons of data and you can afford to do the computation, by all means do. Data can tell you more if you don't put assumptions on it. But often in practice, you actually have some knowledge about what you're working on. I mean, when we're looking for data about this and ask Fred about a data set, then he usually knows I have this object that I understand, and there are these regions that I can't solve. So usually there's stuff you know, and you can use it. So the idea is, if you know these things and you actually need them in order to solve, how can we code them? How can we just tell the computers, this is what I know, and use this in order to solve? We can make more elaborate models. We can make these things move, which is something we're doing in actually the prototype that we're building now. maybe we can look at smarter ways of looking at the deformations. Maybe one day we can even include molecular dynamics into this. We can have better priors controlling the deformations, or maybe some magic from deep learning. And we can use the covariance method or the manifold learning to kind of characterize what should we be doing, like look at the regions where there's heterogeneity and things like that. And the question is, how do you fit all this modeling and all these tools into all these modeling and all these priors into a tool that can actually be flexible enough to accommodate them, and we don't have to rewrite a completely different tool every time someone has this idea of tweaking something small in it. The problem with expectation maximization is that it's the computation is expensive enough for looking at all the orientations, and now we're sort of saying add additional dimensions. So this is making it very expensive, and there are all these methods that people came up with to make this cheaper, right? I mean, we don't actually look at all these different orientations, but it starts to be a question of to what extent can you still do this when you have these sort of flexible models and people can do weird things with them. So how much can you predict what people would do and predict where you want to do, how you want to do this? So directions we're looking at as for several reasons is Monte Carlo, Markov chain Monte Carlo. The classic way of thinking about, so what Monte Carlo does is, where it works well is you have your posterior distribution and you try to sample from that posterior distribution. In our case, it means sampling these hypervolumes, describing an object with all of its heterogeneity. The way it usually works, or the classic Metropolis Hastings algorithms, is you have your current estimate of all your variables. You come up with another estimate, and then there's this, and you compute the likelihood for both. And there's this computation that you do to decide if you keep the current state that you're in or switch to another one. So people usually think about it as perturb the state a bit, but there's actually other ways of doing it. And you can actually, so there's actually many different strategies to implement this type of Monte Carlo, and there are other types of Monte Carlo as well. And one of the nice things you get out of this that's not as relevant for our discussion, but it's also a useful thing, you get some kind of statistics of the solution, because you sample different solutions, so you can get some handle on the variance in your solution and things like that. So there are many different ways, many different types of strategies for how to make these updates. One of them, or several of them, are based on using the gradient. So basically the idea is, instead of trying to perturb your state and see if it's better or not, you actually look at the gradient on all your variables and you say, okay, I'm going to try to walk in this direction, and there's an update rule for do I keep it or not. There are more sophisticated things, like using Hamiltonian Monte Carlo. But this starts to look a little bit like optimization. So there's all these relationships to optimization and things that we know that work, like stochastic gradient descent. And what we're building is basically this idea of, let's put together these models that are sort of generic. They're not completely generic yet. There's software engineering into it, right? But that look at several different objects, what they can do, how they can behave, the relationships between them, have all these different variables that control them. It's kind of not that complicated to add additional priors on, for example, how the CTF between different images behave or something like that. And then what we do is we try to sample hypervolumes and their state from these posteriors. And so that's what we're doing now. And it plays nicely with other methods. So we can formulate ideally ways of trying to put additional priors, maybe even physics, maybe even molecular dynamics into this one day. It's maybe a little bit far from now. But people have done things with molecular dynamics and tying it to to cryo-EM densities, so maybe not that crazy. It doesn't require the exact conditional distribution that you need technically for it to do expectation maximization. So it allows us to do these steps without checking all the different orientation. At least each step is possible without this. We can use a mixture of different strategies. So if you have a great idea for how to update things, or if you can afford to scan over all the different orientations, you can sort of plug this in and as a different type of step. And often, so sometimes when you run into a problem like how far can you push Monte Carlo, you go to these variational inference method that try to approximate kind of what you would be doing there in computationally more efficient ways. So it's kind of the same machinery can be used to look at things that are not purely nice Monte Carlo. So these are results from, again, that's previous prototype. So, and this actually uses these prolates that I didn't talk about. So this is the pretzel. These are images from the pretzel. And this is a reconstruction of the pretzel. This is, these are these variance maps where you can see regions where we would expect to see some action. And as we can see, we can capture a lot of the movement of this, this object. And there's actually kind of an interesting artifact there, which I'm happy to talk about. It's actually kind of interesting local minima, but I won't talk about here. So other things, so this is an actual molecule, and it's hard to see, but we think that there's this kind of motion here where these things are spinning a little bit. And since we had this in the previous example, so we think what we see here is these guys moving a little bit. You can see these two here. They're actually two independent objects. We're not really interpreting it yet, because one of the things we need to do, and that's where we're heading to now with the new prototypes that we're building, is really to take this to higher and higher resolution. And in these, we're only able to use a limited number of images. So it's really, part of it is about scaling this. So we basically threw out everything and rewriting everything from scratch to make it more scalable and allow us to go to higher resolutions. So this is just so I can get into a fight with everyone, but I mean, the point is, you know, I'm trying to explain the differences between the two, and you know how like every map that you make of the world is like really bad. It's not really capturing what projection of the sphere. The other thing is, you know, all these things are on paper. Really, we have to remember that most of the traction we got so far is with these sort of looking at independent objects, okay? And it would also depend on like how things are implemented, et cetera, et cetera, et cetera. But the idea is these independent objects work pretty well for a small set of discrete objects. That's fine. And there are these multi-body techniques now, and they're great if you have rigid objects moving, but maybe not as great if they're not rigid. And there's the covariance methods. They usually need an orientation, I think they were very difficult to interpret until Joachim's talk today. Because it's actually difficult to tell what's going on, because I can show you an example, and if anyone wants, like of what it looks like when you have an object that's moving. How do you see it in covariance? You actually don't see it very well, because you have to know how to choose until you have Joachim's map. There's diffusion maps, which can be very interpretable, and but also needs these orientations. Both of these have a tricky way of dealing with high dimensionality. There's like, we don't have time to talk about the details, but they can't decompose these objects, at least for now. And we think that we can get a lot of these things in these hypermolecules, partly because most of the great ideas can be kind of, you can translate them into this domain. So if there's great ideas about using multi-objects and letting them move, why don't we let them move and let them also deform as they move? One of the nice things about this is that you can sort of adopt things from other methods that really work. So just to summarize this, hypermolecules, well, first these are the questions, and hopefully a way of writing the answer. It's just a way of writing higher dimensional functions, and I showed you one way of writing it, which is using these linear combinations of basis functions, but it can be anything. You can use them to write more complicated, sort of specialized objects that describe what you know about the problem. The other part that go into this is this modeling and writing priors for functions. And again, if you have all the data in the world and you can use and you can compute, just let the data tell you what's going on. But in practice, you might want to put in some kind of modeling, some kind of priors onto what you're computing. And what we're trying to do is find the ways to write these models and priors. And the algorithms that we're looking into is sampling this Monte Carlo that samples these hypermolecules. Each sample is a hypermolecule. So the object with all of its conformations. And we can use many different strategies. It allows us to use these kind of complicated and flexible priors. And I've shown you some prototypes of what we have now that are actually based on these Monte Carlo algorithms. And what we're building now is this new prototype that would be more scalable, better resolution, kind of more generic than the limited ones we had so far. And yeah, so hopefully it will be more flexible and allow us to show more results. I was hoping that I could show a few today, but I think it'll take a couple of more weeks to get something out of it. This is work that with Joachim Anden and with Amit Singer, and James Brofus is joining now with some of the new methods that we're putting into this now in this new prototype. So these are this is the technical report, a paper about this, and there's other things we can talk on Saturday or after the talk, and thank you very much.